Hi, Dr. J here with my guide to partitions. Today we'll be introducing the property that a collection of sets can have called a partition. In order to do so, we'll be using many of the concepts we've discussed earlier, namely subsets, unions, intersections, complements, and so forth. But before we get into partitions, we have to first describe a couple of other properties, namely disjoint and pairwise disjoint. So let's get started. Two sets are called disjoint if their intersection is the empty set. Mathematically, we would write this: A intersection B is equal to the empty set. Another way to say this is that those two sets have no elements that are in common. So here's some examples. So here's first a set of examples that are disjoint and then a set of examples that are not disjoint. So the sets here that just include the singletons 1 and 2. That is, the first set includes just the number 1, and the second set just the number 2. Those sets are disjoint because there are no elements in common between those two sets. The second example here has the sets of integers 1 through 9, and then the second set has the integers 0 and 10. And again, there's no elements in common between those two sets, and therefore these two sets are disjoint. Here's an example using an interval, or two different intervals for our two different sets. The first one has all of the negative integers, and the second set has all of the non-negative integers. And just even in the English words I used to describe that, you might be able to tell that these two should be disjoint, that is, they have no elements in common. For some examples of sets that are not disjoint, we have these. So the first set has the integers 1 and 2, and the second set has integers 2 and 3. If you take their intersection, you get the number 2, which is not the empty set, and therefore these two are not disjoint. Here with our important sets, we have the natural numbers and we have the integers. Natural numbers denoted by the letter N and the integers denoted by the letter Z. And because both of these have the positive integers, then their intersection would be those positive integers. In this case, since we've defined natural numbers to include 0, our intersection would also include the number 0. But the main point here is that it's not the empty set, and therefore these two are not disjoint. Here's an example where we've taken the interval from the disjoint example, and we've now just included 0 in the first interval, and therefore when you take the intersection of these two intervals, you're left with the number 0 in that set, and therefore because that's not the empty set, these two are not disjoint. So again, disjoint just means that two sets have at least one element in common. If we want to represent this in our Venn diagrams, we can do it like this. Just as a quick reminder, our Venn diagrams describe our sets by placing areas, in this case circles, to indicate our two sets. And if there are any elements that are in common between those two sets, there will be overlapping areas of the circles. Because these two circles are non-overlapping, that means that their intersection is empty, i.e. that they have no elements in common. And so as a visual representation of disjoint, this is the picture that you should have in mind. Now we can extend this idea to more than two sets. And if we have a collection of sets, that collection is said to be pairwise disjoint if every pair in that collection is disjoint. So another way to write that mathematically is to say, all right, let's imagine we have this collection of sets called A1, A2, and so forth, possibly an infinite number of them. And if we can take every pair of sets, their intersection is empty. So that is AI intersection AG is equal to the empty set for all I not equal to J. If you haven't seen it before, that upside down A symbol represents the English words for all or for every. And so this just says, all right, take any I and J, except that they can't be the same number, and the intersection between those two sets, AI and AJ, is the empty set. So here's some examples of sets or collections of sets that are pairwise disjoint. Now I've noticed here I've written this in a new sort of set notation, right? So I have curly braces that represent my individual sets, say the set 1, 2, 3, and the set 4, 5, 6. But these sets are within some further curly braces, right? Because a collection of sets is really a set of sets. Because if you remember our definition of a set was just a collection of things. So in this case, we have a collection of sets. And so it's a little bit tough to understand the first time, but this just means that the elements of this collection or the elements of this set are in fact sets. So the elements of this set are the sets that contain 1, 2, 3, then 4, 5, 6, 7, 8, 9, and 10, 11, 12. So now the key thing with this page is to say, all right, now let's take any pair. So I have to take the pair of the first and the second, the first and the third, the first and the fourth, the second and third, second and fourth, and third and the fourth. So take all those pairs and take their intersection. And I have to check whether that intersection is empty. A perhaps easier way to think about this is just to say, are there any elements that are in more than one set? Right? And in this case, there's no elements that are in more than one set. And therefore, if you take any pair, you are going to get an intersection that is empty. Here's a second example. The second example, each of the individual sets just has one element in them. And those elements are the positive integers. So the first set in our collection is the set that just has the number 1. The second set just has the number 2. Third set just has the number 3, and so forth. All right, now an infinite number of them. But again, if I take any pair here, they will have no elements in common because none of the numbers are repeated in these set of sets. Here's a third example. We now have intervals are what comprise our elements in this overall collection or set. The first interval here is 0, 1, then 1, 2, 2, 3, and so forth. Because all of these intervals are open intervals, that is, they do not include the endpoints, if you take any pair and you take their intersection, they are going to have no elements in common, and therefore their intersection will be the empty set. Here's some examples that are not pairwise disjoint. So I took the first bullet point where we had a set of sets that is pairwise disjoint, but now I just changed one number. I changed the 10 into a 9. And because I did that, if we take the intersection between the third and fourth sets, that is between the numbers 7, 8, 9, or the set of numbers 7, 8, 9, and the set of numbers 9, 11, and 12, we will get their intersection to be 9, right? Which is not the empty set. Therefore, this collection is not pairwise disjoint. Here's a next example. Here we have each element in this collection of sets is a set that includes two numbers. It includes integers 1, 2, and then 2, 3, and then 3, 4, and so forth. Now we can quickly see here that if we take the intersection between those first two sets, we will get the number 2, or we'll get a set that includes number 2, and only number 2, but the key is that it's not the empty set. And because it's not the empty set, this collection of sets is not pairwise disjoint. A final example, we just took our pairwise disjoint example with open intervals, and we changed those open intervals into closed intervals. And because we are now including the endpoints, when you take the intersection between any of these intervals that are next to each other, the common endpoint will be the intersection of those two sets, and therefore will not be the empty set. So for instance, if you take the intersection between the closed interval 0, 1 and the closed interval 1, 2, you will get the number 1, or you'll get a set that includes number 1, which is not the empty set, and therefore not pairwise disjoint. As a Venn diagram, we can see pairwise disjoint as this visual depiction here, which includes 8 sets. And the key is that none of our sets have any area that overlaps. And because they have no area that overlaps, the intersection between any two pair will be the empty set. Now, we've gotten to the point where we can define a partition. So a collection of sets is a partition of S. So notice here that we need another set for this collection of sets to be a partition of. Typically, you'll be interested in partitions of the universal set, and so we're using that notation here, but in principle, it could be a partition of any set that you would like. So it is a partition, this collection is a partition of S. If, there's going to be 3 rules here. If none of the sets is the empty set, if the collection of sets is pairwise disjoint, and thirdly, if their union is S. Written mathematically, we can take a collection of sets, say A1, A2, and so forth. It's a partition of S if for every I, AI is not equal to the empty set. For every pair where I is not equal to J, the intersection of AI and AJ is the empty set. And finally, if the union of A1, A2, A3, and so forth is the entire set S. Here's a page worth of examples. And for these examples, I'm going to split it up into 3 different groups where I'm going to take a set S and show you a few partitions of that set S and then change set S and so forth. So we're starting here with the set S, the universal set for the purpose of this slide right here, or this set of examples, are just the integers 1, 2, 3, 4, 5, 6. So the set just includes those integers. And so one way that we could create a partition here is just to create sets that have each of those individual elements. So we have the first set that just includes the element 1, the second set just includes 2, and so forth on up to 6. And this collection of sets satisfies all of those properties, namely that empty set is not in any of these, that they're pairwise disjoint because the intersection of every pair is empty, and finally that if you take the union of this collection of sets, you get back the full universal set S, in this case the integers 1, 2, 3, 4, 5, 6. Now we can take partitions many ways, so here's another way we could take a partition. Here the partition is taking the odd numbers in that collection and then taking the even numbers in that collection. So the odd number is 1, 3, 5 and the even number is 2, 4, 6. Again, the empty set's not here. The intersection between these two is the empty set and the union is the entire set above. Now this example provides an example of a more general idea. That is that you can always construct a partition by taking a set and taking its complement. And those two sets will create a partition of the set that you wanted to create a partition of. Here's a final example, a trivial example. This trivial example shows that you can always create a partition just by taking the set itself. So in this case, there's only one element in this collection of sets, and in this collection, the element is the set that includes the elements 1, 2, 3, 4, 5, 6. Here is the natural numbers that, again, for our definition, we're including 0. And for this definition, we have the singletons. So that is, each set here includes just one element. So you start with just the set that includes 0, then just the set that includes 1, and just set that just includes 2, and so forth, and that creates a partition of n. We again go with the even odd example. So in this case, we have a set that includes all the even numbers. Let's say all the even non-negative integers. And then we have a set that includes all the odd integers, positive odd integers. And that creates a partition of the natural numbers. Here we have another way to do it, just by taking pairs of numbers and increasing in that set by 2. So the set that includes 0, 1, the set that includes 2, 3, set that includes 4, 5, and so on. Here's a partition of our positive real numbers. So we take the half open intervals 0, 1, where we are always including the right endpoint, and we just shift those intervals by 1, or we shift the endpoints of those intervals each time by 1. So we have the interval 0, 1, interval 2, 1, 2, interval 2, 3, and so forth. And now you should verify to yourself that this follows all the properties of a partition, and therefore is a partition. Here we have a slightly modified version of that, where we wanted, for some reason, to say have all open intervals. So we have all the open intervals, but then we have to include the singletons that are those positive integers. So here's just the main point of this page is to show you that in order to create a partition, we can do so in typically many different ways. Let's get some visual representation of a partition. So first off, I'm going to show you an example that's not a partition. So in this case, we have our example from the pairwise disjoint. So we know that it satisfies that property. None of these sets are empty. So it satisfies the first two properties, but does not satisfy the third property, namely that the union of these sets must be the entire set that we're trying to take a partition of, in this case, a partition of S. And the way that we can tell from this Venn diagram that it does not create a partition is that we can see white space. That is, if we had a partition, it would completely color that entire universal set. And now we can't actually do that with circles, right? So there's no way to fill this space with circles. So now we need a different polygon. So we're going to use, as an example, rectangles. So in this example, we have 5 rectangles, A, B, C, D, and E. And now I have to tell you, because it's not obvious from the diagram, but none of these rectangles overlap. All right, so A is just the orange area you can see, B is just the light blue area, C is the green area, D is the yellow area, and E is the darker blue area. And these rectangles now form a partition because none of them are empty. They don't overlap, so the intersection of any pair is the empty set. And thirdly, their union is the entire universal set. That is, there's no white space in this picture. Now again, we can create partitions in different ways. And here's one example way that I described to you before, where we can create a partition by taking a subset and its complement as the 2 elements in our collection to create that partition. So in this case, we have the set A, that's the orange circle, and we have its complement, that's the pinkish area that's outside of the circle but within the rectangle. And if we take A and A's complement, that creates a partition. Again, because neither of them are empty, their intersection is empty, and their union is the entire universal set. Here's another example where we can take a subset of S, but now the subset itself is a bit more complicated than in the last picture. This subset is composed of distinct elements, distinct areas, let's say, of this Venn diagram. So if you want to in your mind, you could be thinking about enumerating these circles. Call one A1, and the next one A2, and A3, and so forth, up to A5, I guess. And now the set A is defined to be the union of each of those 5 circles. But nonetheless, in order to create a partition, we can use that union, that is those 5 circles. We can take the complement of those 5 circles, which is the pinkish area. And again, now we have a partition by taking a set, that is the 5 circles, and its complement. All right, so here's a summary. So we introduced today the idea of being disjoint, the pairwise disjoint, and a partition. These were all properties of a collection of sets. I want to mention now that oftentimes the definition of a partition does not include this first point. It does not include the that you cannot have the empty set. We included it here just because if you don't have that first one, you can get some, they're not really so weird, but somewhat pointless partitions that just include the empty set or includes the empty set multiple times, and it really doesn't add any value. So just for simplicity, we included the lack of an empty set. Finally, here's 2 pictures of what a partition could look like. Next time, we have our last video on sets, and we're going to talk about the cardinality of sets. As a reminder, the cardinality, it discusses how big the set is in terms of how many elements it has. And we've already discussed these a little bit, but sets will either be finite, let's say sets that we're interested in will either be finite, countably infinite, or uncountably infinite. Until next time, have a great one.